So good morning, everybody. Welcome back to Math 210, that's Calculus 1. And so today we're going to be talking about the chain rule. And like usual, I do have a series, I do have a video or two on this. I've got actually 3 videos on this topic, one kind of introducing it, one giving the proof of the chain rule, and one showing some examples. It's about 25 minutes total. So if you've studied those videos, you may feel like you're in a pretty good place. And I definitely hope that you watch before class, but this is something that I want to go over carefully, so I will redo some of the things that I did in the videos, just because it's so important. But definitely if you watch them beforehand, I think it'll help you out, because I recorded those a couple years ago, and my presentation might be a little bit different for those. It's definitely more careful, whereas here it's more informal and relaxed, and we do more examples. So if you didn't get a chance to watch it, go check that out after class. So today is about the chain rule, learning objectives, understanding what the chain rule is, understanding the 2 different ways to notate it. In order to do this, we're also going to have to understand how to take 2 functions and take the composition of those 2 functions. And before just jumping straight into it, trying to state a theorem or give you a proof, I want to play around with some examples to try and give us some context. So the light turned off on me. I'll try to, it's on a motion sensor there. To try and give us some context. So in the first part, we're gonna get some practice taking compositions of functions, and I think we'll also just take some derivatives without the chain rule and see if we can predict what should happen. So let's get into it. So what do I mean when I say a composition of 2 functions? So far, if you're given like 2 functions, like say f of x equals, I don't know, let's start with x squared. And take another function, maybe g of x equals 2x. There are certain things we know. So we could use the power rule to take the derivative of f of x. We could use the power rule to take the derivative of g of x. If we wanted to multiply these functions together to take f times g, we could just do that and get 2x cubed and then take the derivative, and that would be fine. Or we know about the product rule, which would also let us take the derivative of f times g, and that's fine. But there's one other way to combine functions. Well, I mentioned multiplying them together. Certainly you could add them together. You could take f plus g. The derivative of that is just going to be the sum of the derivatives. There's one other way that we like to combine or amalgamate functions together, and that's with the composition. So we write that as f composed with g. That's the formal way to write a composition of functions. And what it literally means is f, and then instead of plugging in x, plug in g of x. And so in this particular case, it's kind of a straightforward example. We'll get to more, we'll get to other examples later on in the class, but in this particular case, what do we get? So we're plugging in g of x, so we're taking f of 2x, and so we are taking 2x squared, which you could also rewrite as 4 times x squared. And so I want to make a chart of different things we could do for f and for g, and then what's the derivative of f, what's the derivative of g. So I should give my, yeah, okay, that's fine. So I'll give myself space to write down the derivatives. And I'll give myself space to write down the composition. And I'll give myself space to write down the derivative of the composition. And so as we go through some of these examples, what I want you to do is to try to use the examples to try to predict, like, is there a formula or a way that you can predict what's going to be the derivative of the composition based on knowing the derivatives of the original functions? Like, see if you notice a pattern. That's what I'm saying. And of course, ask me any questions as you have them. See if I can get one of these. Yeah, I wish I could reduce the glare for you there, but I can't make that happen with the way the lights are set up. So here, f prime, using the power rule, that's just going to be 2x. And here, g prime, that's just going to be 2. On the other hand, f composed with g is equal to 4 times x squared. And now the derivative of f composed with g, that's the derivative of 4 times x squared. So using the power rule, that's going to be 8 times x is my answer. In my video lecture, I said something like, if you think of f of x equals x squared as a movie, then plugging in g of x, taking the composition, is like playing that movie twice as fast. And so I'll notice that this is looks like 4 times. Looks like 4 times the derivative of f of x. But it feels like it should just be twice as fast. So what's going on with that? Well, we'll explain that in a little bit. But think about that. Let's do more examples. So let's take f of x equals square root of x. I'll keep g of x the same. And so f prime of x, think for a minute, what's going to be f prime of x? So you can do that based on the knowledge that we've got so far. You just have to do a little algebra trick. So after letting you think about that for a moment, the algebra trick I had in mind was that the square root of x. Another way to write that is x to the 1/2. So you can use the power rule to do this, and the derivative is going to be then 1/2 times x to the 1/2 minus 1. That's minus 1/2, which you can now rewrite as 1 over 2 times square root of x. And what's the composition? F composed with g, that's f, plug in g of x, that's f of 2x. So that's the square root of 2x. And now what's going to be the derivative of that composition? Well, you might raise your voice a little bit and say, well, we don't really know how to take the derivative of square root of 2 times x, right? But here, algebra can save you again, because you can rewrite this as the square root of 2 times the square root of x. And so the derivative of the composition, the derivative of square root of 2 times square root of x, is now going to be the square root of 2 times the derivative of the square root of x, which we've already calculated. So this is now going to be the square root of 2 times 1 over 2 times root x. So this is going to be root 2 over 2 times 1 over root x. And I'm thinking about, can I maybe rewrite this in a nicer way? Well, maybe I'll save that for later. But right, so at the beginning of class, any questions about how to take the composition or how to take the derivatives, or like what am I doing to take the composition of the derivative? So let's get on that same baseline. So pause for any questions or comments. Okay. So at this point, maybe the best thing to do is to say, well, let's go ahead and state what the chain rule is, and try to compare it to what we've been doing and see if it matches. And so the chain rule says that if you want to take the derivative of a composition, so that is to say, like, the derivative of f of g of x, or another way to write it, f composed with g prime of x, right? So this derivative, you want to take the derivative of a composition of functions. And there's an assumption you have to make. You have to assume that f is already a differentiable function and that g is already a differentiable function. But if those two things are true, then the composition will be differentiable. And here's what the chain rule says. It says that it's going to be equal to the product of the derivative of f at the point g of x times the derivative of g of x. And so, well, like what's going on there? Like eventually I'll give you an idea of like why this is true from like an algebra or limit perspective. So like I'll show you sort of like what's the proof. But what's the idea? Remember, like f composed with g, that's f of g of x. So you're taking the derivative of this composition, right? So as x changes, what's the rate of change of the composition? That's what you're being asked. So as x changes, you have to take into account the fact that f of x is changing and that g of x is changing. And so think of yourself as starting at a particular point, like x naught, or like x equals 2. And as x changes, like a little bit bigger than 2, a little bit less than 2, you're still going to be centered around this place, g of x. So it makes sense that the rate of change of f at the point g of x should show up. Like, it makes sense to me that that should show up. One question people ask is, why isn't it like f prime of x? Well, because you're already starting with a composition, f of g of x, and then you're letting x vary. So that'll make g of x vary, which will mean that you'll pick up something that looks like a derivative of f at the point. But why this extra factor? Because x is just changing, a little bit from here to there, but this will also cause a change in g of x. So it's not just like function f of x that's changing, it's also function g of x. So in order to account for like the totality of the rate of change of the composition, you do need something that separately involves the derivative of f and separately involves the derivative of g. And the cool thing is that you can just multiply them together, and that's the answer. But the other thing about that is that it's not immediately clear that this is what you get when you multiply them together. So maybe we should check that with this example that we've already done and calculated. Right? Because we've already calculated the composition of these two functions and taken its derivative. If it doesn't match what that formula says, then the formula isn't very good, or perhaps I just made a mistake somewhere. So let's try to take this and calculate using this formula and see if it matches. Hope I'm not standing in front of the camera too much. Yeah, so f composed with g is the square root of 2 times x. It's square root of 2 times square root of x. Here's the derivative of that. On the other hand, it's supposed to be derivative of f. That's what I want to plug in. Derivative of f, but plug in g of x. So here's the derivative of f, right? It's f prime of x. And I'm plugging in g of x. So I'm taking 1 over 2 times the square root of x, but I'm plugging in g of x. So I'm plugging in 2x. And I'm multiplying this by the derivative of g of x. And the derivative of g of x is just equal to 2. And the 2's are going to cancel. And this is just going to give me 1 over square root of 2x. So, is that different? Is that really different? No, it's not, because root 2 over 2, what's that equal to? Well, 2 is equal to root 2 squared. It's kind of like a tongue twister, right? And then I could just cancel one of the factors of root 2. So what I would be left with is 1 over root 2 times root x, which I could then combine back and say that's 1 over square root of 2x. So it takes a little bit of algebra, but these answers are just presented a little bit differently. Strictly speaking, this way is a little bit more proper, because like when you simplify rational expressions, you typically don't put a square root of a constant in the denominator. But here in calculus, I don't really care if you write expressions like this, even though that one's a little bit more simple. I'm not going to really count off points for that. So the important thing is really, recognizing this is composition of functions, taking derivative. This is the derivative of f. I'm plugging in g of x, multiplying it by g prime of x. Any questions or comments on that? Let's compare it to the first example that I did with f of x equals x squared. And then f prime of x is 2x. And then the composition was f of 2x, which was 2x squared, which was 4x squared. And then we saw the derivative was 8x. And so if you try to apply the chain rule to calculate this, f prime, plug in g of x. So f prime of x is 2x. Plug in g of x. So 2x, but you're going to substitute in 2x, right? Here's your function, f prime of x. Substitute in g of x into that. And now you're multiplying by g prime of x. So you're multiplying by 2. 2 times 2x times 2 is 8x. So when I was saying, like, if you're playing the movie twice as fast by substituting in 2x instead of 2, you should think that you're multiplying by 2. You know, you're multiplying by the speed at which you increased. And you are. There it is. So where does the 8x come from? It's because 8x is equal to f prime of g of x. So it's not 2x times 2, it's 4x times 2, because you're not taking the derivative of f at the point x, you're taking the derivative of f at the point 2x. So that kind of solves that original mystery. So it is, you know, by substituting x for 2x, you are speeding up the derivative by 2, but you're also changing the point at which you take that derivative from x to 2x. That's the idea. Let me give you one to practice. Let's take f of x equals sine of x, g of x equals 2x squared. So f of g of x is therefore sine of 2x squared. And so on like homework or a test or something, you'll just be presented with a function like this and say take the derivative. So you'll need to be able to identify for yourself that this is a composition of functions. You'll need to identify for yourself f of x as sine of x, like g of x is 2x squared. And then you'll need to remember the statement of the chain rule. So you'll need to put those pieces together when you're doing this. And I'll give you a couple moments. Please fill in f prime of x, g prime of x, and then please use the chain rule to find the derivative of sine of 2x squared. Let me know if you've got any questions. Okay, after giving you a few moments, I'll share my result too. So we remember from last time that the derivative of sine of x is cosine of x, and the derivative of g of x, this is going to be 4 times x. Therefore, the derivative of sine of 2x squared is equal to derivative of f, that's cosine, plug in x, that's 2x squared. Times derivative of g of x, which is 4x. So there's our answer. Derivative of sine of 2x squared is cosine two x squared times 4 of x. Okay. Let's do one more. Let's take f of x equal to square root of x. Let's take g of x equals x to the 4 plus 1. Take a moment to please work that out and chat me if you've got any questions. Okay, after letting you think for a moment. So we need f prime of x. We've seen that before. That's 1 over 2 root x. G prime of x, doing it term by term, power rule tells me it's 4x cubed, and then plus 0, because derivative of 1 is equal to 0. The composition of the two functions is equal to square root of x to the 4th plus 1. So just as a reminder, when you're doing homework exercises, it'll be something like, okay, here's a function, take the derivative. And then plugging it into the chain rule. So f prime composed with g of x. So that's f prime, that's 1 over 2 square root of g of x. G of x is x to the 4th plus 1. And I'm now multiplying by g prime of x, which is 4x cubed. There's another way you can like conceptualize this. So like if you think of this as like x to the 4th plus 1, and you don't have to do this, but if you think of this as like x to the 4th plus 1 to the 1/2, you want to take that derivative, you can kind of treat what's inside here like as its own variable. So you can write this as like 1/2 x to the fourth plus 1 to the minus 1/2, and now you multiply by the inside function, by the derivative of the inside function, excuse me, which is 3 times, excuse me, which is 4 times x cubed. So you see what I did? Like thinking of this as a separate variable and then using the power rule would give me 1/2 variable to the minus 1/2. It's just power rule. And then multiplying by the derivative of that variable, the derivative of the inside function, if you like, then gave me the result. So rewriting the algebra so that negative 1/2 is 1/2 root x to the fourth plus 1 times 4x cubed. You can see that I get the same thing. And that's the way that scientists and mathematicians will often try to do this chain rule in their head. You know, as you're progressing forward, you're not necessarily going to be so detailed as to write out these 4 things, although if you do, you'll make far fewer mistakes. But what you can do is you look at something like this and you say, oh, okay, yeah. 1/2 inside function to the minus function to the minus 1/2, then take the derivative. And I'll also take this time to point out that there is another way to notate this. So I'm using this prime notation. But there's another notation for how to take a derivative. So like if you say, like y equals f composed with g. So y is a function of x, right? And you're trying to take this derivative. So you're trying to find dy dx. Remember, that's like Leibniz notation. So there's a way that you can rewrite. So in fact, if you're setting y equals f composed with g, and remember how I was talking about taking the inside function g and like making it its own variable? You can kind of formalize that a little bit. You can just say, well, let's write u equals g of x, just for the purposes of this notation. And I want to convert this into Leibniz notation. So this left-hand side is dy dx. And then f of g of x, that's like f of u. And so f prime of g of x is like f prime of u, which is the same thing as writing. Isn't that the same thing as writing like dy du? So you're taking the derivative with respect to the variable u, just like I was doing here, right? Like thinking of this as like u to the 1/2, and then just taking the derivative. So dy dx is like equal to dy du times g prime of x, but g prime of x will be du dx. So this is the Leibniz version of the chain rule. So they both mean exactly the same thing, but one of them is written with primes, and one of them is written with this notation where y equals f composed with g, g is equal to u, so you might write y is thinking of the inside function as its own variable. Then dy dx is going to be like dy du times du dx. And I'll prove to you that this is always going to give you the same answer. Or at least I'll show it with this example. Because if, let's take y equal to the square root of x to the fourth plus 1. Right, that was the composition of functions. And in this case, u was equal to g of x, so u is equal to x to the fourth plus 1. So y equals square root of u, y equals f of u. Dy dx, that's the derivative of this with respect to x. So let's take dy du as a function of u. I'll go ahead and write it again. So y is equal to square root of x to the fourth plus 1. Y is equal to the square root of u. Just with that substitution, right? So dy du is just equal to 1 over 2 times the square root of u. And du dx is equal to 4x cubed. Of course, you wouldn't leave your answer right like that. You wouldn't leave it with the u just sitting there because you want to write your answer in terms of x. So you'd make sure to keep it as 2 times the square root of x to the fourth plus 1. I mean, u is x to the fourth plus 1 times 4x cubed. But that's the relationship. So when someone is saying dy du, that's what they're saying. Like you substitute g of x with u, take the derivative, and then plug g of x back in. That's what this is supposed to mean. That's what that's supposed to mean. And then you're multiplying it by du dx. And the cool way that you can remember this is even though these aren't literally fractions, they're limits of fractions, they're limits of difference quotients, the cool way you can remember this is you can think about the du's just like canceling, you know? And then you'll be left with dy dx. So that's how you can always memorize the chain rule in your mind. Like dy dx, well, what's your inside function? Call it u. It's going to be dy du dx. And so this Leibniz version is probably the easiest to remember, quite frankly, and it's probably the easiest to work with when computing problems. Whereas this one is easier when you're trying to like prove things, if you go on into higher mathematics. Any questions or comments on any of that? So I'll briefly go over the demonstration of like the formal demonstration of why the chain rule is true. But I do have a video on this, so I'll try not to take too long to do it, and you can watch that video for the proof. But like so we're trying to take this left-hand side and show that it's equal to the right-hand side, and when you're trying to demonstrate that for the first time, not just do a calculation, but demonstrate that the formula itself is true, you really only have the recourse of going back to the definition. And so you remember that the definition of derivative is limit as h goes to 0 of f composed with g of x plus h. So that's f of g x plus h, right, minus f of g of x. So we're taking the derivative of f composed with g, so we have to plug in x plus h, and then just subtract plugging in x, and then we're dividing by h. And we're wanting to get something that kind of looks like a product. And so that motivates my next step. So I'm going to try to, maybe I can just go ahead and write it here. I think I want to try to multiply and divide by what? Like g of x plus h minus g of x divided by g of x plus h minus g of x. I mean, you're allowed to multiply and divide by the same thing so long as it's not equal to 0. And let's just assume that this difference is not equal to 0 for the sake of argument. If it was, you have to do something more technical. That's for a different class. Just trying to give the idea. So if I rearrange this, like bring the h from here to there and the g of x plus h minus g of x from here to there, end up with limit as h goes to 0 of this numerator. And then times, what do we got here, like g of x plus h minus g of x over h. So limit h goes to 0 of this entire thing. And the limit law is going to let you break it up as limit of this times limit of that. And this limit is definitely g prime of x. That's the definition of g prime of x. Whereas this limit, we need to work and try to show that that's equal to f prime of g of x. And so, like, how can we do that? I think that the trick is to make a little substitution, like you make a new variable, like you call it k, and you call k by, this is your definition. Define a new variable k to be equal to g of x plus h minus g of x. I believe is what you want. And since g is differentiable, since g is a continuous function, as h goes to 0, k will also go to 0, right? Because as h goes to 0, this tends towards g of x minus g of x, so k will also go to 0. So I'm able to introduce variable k, and then h going to 0 will be the same thing as k going to 0. It's kind of important. And if I try to rewrite this limit right here, I can say limit as k goes to 0, because h going to 0 is the same thing as k going to 0. And what do I get? Well, g of x plus h minus g of x was k, so that's just the denominator. So my logic is I'm breaking this up into two limits, this limit and that limit. And this limit was g prime of x, and this limit is I'm rewriting in terms of k. And so what's the numerator? Well, g of x plus h, by definition there, g of x plus h is k plus g of x. So bringing that g of x to the other side. Or in other words, it's g of x plus k. Minus, well, f of g of x. I mean, there's no h in here, so it just stays what it is. So now I've just rewritten this in terms of variable k. This limit was g prime of x. But now this is the definition of f prime of g of x. It's the definition of f prime of g of x. So it's quite beautiful, really, by doing this trick of multiplying and dividing by the same quantity. You're allowing yourself to see the difference quotient for f of g of x and the difference quotient for g of x. Of course, to really see this one, you have to do a little bit of a change of variable, changing variable from h to k. But that is a legitimate change. In an analysis class, you can formally see an epsilon delta proof that does it. It's actually kind of hard to write down every single detail, but this is absolutely the idea. It's what makes it work. This is what proves the chain rule. Okay, so the three things that are really important what are they? The composition of functions and statement of the chain rule. Stating the chain rule and working with it with the Leibniz notation, the dy dx notation. And also understanding the reasoning, or like the reasoning why it's true, understanding the proof of that chain rule. And with 5 minutes left, maybe there's time for like one more example. But any questions before I do one more example? Hey, that's all good. No problem. Okay, so yeah, this is from the book, but I didn't do it in advance. Let's try to see if we can work it out. It's kind of like a physical example. So it says, suppose you have a spherical balloon of radius r. So the idea is you're blowing up a balloon. And suppose that as you're blowing up the balloon, the radius r increases at a rate of, say, 3 centimeters per second. So that's given to you. Blowing up the spherical balloon, the radius r is increasing at a rate of 3 centimeters per second. At what rate is the volume of the balloon increasing? So what's the rate of increase? This is a classic word problem. So what's the rate of increase of the volume when the radius is 10 centimeters? So what's going on with this? Let me try to explain what's going on with this. So you're blowing up the balloon, and so the radius is changing with time. So think about this radius increasing at a rate of 3 centimeters per second, right? That's your clue, that the variable with which it's increasing, with respect to which it's increasing, is time. So another way to write this is that dr dt is equal to 3 centimeters per second. The rate of change of r with respect to time is constant. It's equal to 3. I know that the volume. I know that the volume of a sphere is what is it? 4/3 pi r cubed. I mean, if you work with that enough, you'll memorize it too. But I think the formulas are in your book, and certainly find the formula on Wikipedia. That's fine. And you're being asked, what is the rate of increase of v when r is equal to 10? And so you have to translate this into mathematics. And so the best way to do this is really with Leibniz notation. It's like dv, dr, rate of increase of v with respect to r when r is equal to 10. The other way to state it is you're looking for v prime of 10, right? Those are two equivalent ways of stating the same information. Rate of increase when r is equal to 10. How can you do this? Because you've got v as a function of r, and you've got r as a function of t. What's the rate of increase when r is equal to 10? So you can use the chain rule for this. So this is going to be I'm messing this up a little bit in my mind. So what is I misstated what this was asking for, because what is the rate of increase of v when r is equal to 10? So this rate of increase, this rate refers to time. So it's actually dv dt. Of course, you're blowing up the balloon and the volume is increasing as time increases. That's the point. And you know the rate of change of the radius with respect to time. You've got a formula for the volume, so you can calculate the rate of change of the volume with respect to radius. But how can you find the rate of change of the volume with respect to time? That's the point. Yeah, so sorry, I mislabeled the variable there. The disadvantage of this notation is that you can't see the variable, so you just write v prime, and it's like, does this prime refer to t or refer to r? So yeah, this notation doesn't really work very well because this should refer to t, but then it's not t that's equal to 10, it's r that's equal to 10. So what could you even put in here? You know, you'd have to put in like v prime of, yeah, it's hard to even imagine how you could write that. So like this notation is the one you want because you're taking volume with respect to time at r equals 10. So that's why Leibniz liked this notation. And I know I'm going a little bit over, I apologize, but it's a concept that's worth explaining. And so chain rule is going to say this is going to be equal to dv dr times dr dt. And you know that it was like r equals 10, and this is dr dt at whatever time gave you r equals 10, but dr dt is constant, it's equal to 3 no matter what. So this is like dv dr at r equals 10 times 3. And so you just need to take the derivative of v with respect to r. And so that's going to give you like 3 times 4/3, that's 4 times pi times r squared. So you plug that in, and when you're plugging in r equals 10, dv dr, r equals 10. That just means plug in r equals 10. So it's 4 pi times 100. It's 400 times pi. So your answer then is 400 times pi times 3. So your answer is 1200 pi centimeters cubed per second. Because the volume over time was centimeters cubed per second. So that's your scientific application of rate of change of a quantity with respect to time when you have a formula that tells you rate of change of a quantity with respect to a different variable. You can put them together using the chain rule. Yeah, so sorry for going a couple minutes over. What I've just introduced is going to be the topic for the next lecture. And so it's going to involve like lots of applications of the chain rule. And I think students traditionally, this is like the first place where they really start to struggle in this class. So just be aware of that. I've got some videos online that I'll show you also, and we'll do a lot of examples next time. So definitely give yourself some extra study time over the next couple of days if you can. So thank you, everybody. Have a great day. Sorry for going a couple minutes over.